Hello students, let us learn phenol. Preparation of phenol can be done in 4 ways: from haloarenes, which we have already done before, from benzene sulfonic acid, third one is from benzene diazonium salts, and lastly from cumene, which is the industrial method of preparation. Now method number 1 is already done in the chapter haloarene. So you know that from when haloarenes are very difficult to undergo nucleophilic substitution reaction. I hope you remember there were several reasons. One of the reasons is because of resonance. The carbon halogen bond is partially double, so it is very difficult to break. There are other reasons too. So when it is treated with NaOH, since the reaction is difficult, it will require drastic condition. So it demands 623 Kelvin and 300 atmospheric pressure. Then in the beginning, sodium phenoxide is formed because phenol is acidic and NaOH is a base. So acid-base reaction takes place to form the salt of phenol, that is sodium phenoxide. You may write down the name of this, sodium phenoxide. So to get phenol from its salt, you have to add acid, maybe HCl or H2SO4, dilute, and you get phenol. So this is the Dow's process, we have learned it before. Industrially it is not very feasible because to attain 623 Kelvin and 3 atmospheric pressure is not an easy task. The second method, which is also your exercise question 11.12, from benzene sulfonic acid. Actually benzene sulfonic acid is this, okay, but how do we get benzene sulfonic acid? Benzene sulfonic acid we get by treating benzene with concentrated sulfuric acid and nitric acid, concentrated sulfuric acid, which is known as oleum, and the reaction is known as sulfonation reaction. So benzene sulfonic acid, when treated with sodium hydroxide, you get sodium phenoxide, which upon hydrolysis give you back phenol. So the two steps we have combined together by writing 1 and 2 over the arrow. Third method is from benzene diazonium salts, you know, BDC in short we call it. Now BDC cannot be prepared beforehand, cannot be stored because it is very unstable. So how do we prepare BDC? We prepare it from aniline. Now what is aniline? Aniline is benzene ring with NH2. So when aniline is treated with sodium nitrite and HCl at very low temperature, 0 to 5 degrees, instead of sodium nitrate and HCl, you may find written nitrous acid also. So BDC is formed, which upon treatment with just warm water gives you phenol. The last method, that is industrial method, is from cumene. The cumene is actually isopropyl benzene, and IUPAC name is 2-phenyl propane. So cumene, when left in the open air, it undergoes oxidation from the atmospheric oxygen and it forms cumene hydroperoxide. Now if you remember, peroxide linkage is oxygen-oxygen single bond linkage is called peroxide linkage. So here between two CH3s, you can see I have written this CH3 here and this CH3 I have written here, and in between C and H you get this OO, that is peroxide linkage. That's how you remember how to write cumene hydroperoxide. So when cumene hydroperoxide is hydrolyzed with sulfuric acid, you get phenol, and the byproduct formed is acetone. So how do we get phenol? It's shown with the dotted line, you can see here. Sorry, the dotted line is not properly drawn. It should have been here. And the byproduct acetone is also very important reagent, and it is sold in the market. So this is very cost effective method because oxygen we are using from the atmosphere, for which we need not pay any money. Sulfuric acid is easily available, and both the products are equally important in the market, so they sell off very well. So the person who is setting up the industry is making good money. So physical property of phenol, as I have said, please do self study. Next we move to chemical properties of phenol. Just like alcohol, phenol also undergoes reactions involving cleavage of OH bond. But unlike alcohols, phenols do not undergo reactions involving cleavage of COH bond because of its strong resonance. The next set of reaction is electrophilic substitution reaction, and there are some name reactions, okay, performed by some specific people. So they are in honor of their name. Then the reactions are named as Kolbe's reaction, Raymer-Tiemann reaction, and then we have one reduction reaction and oxidation. So let's begin with one by one. Phenol, the first set of reactions involving cleavage of OH bond, and just like alcohol, the first property is acidic property. And you can check, phenol is a stronger acid than alcohol. So in alcohol we have seen alcohols react only with sodium or active metals to liberate hydrogen. The other two properties of acids are not exhibited by alcohols. But phenol, being little stronger acid, it reacts with active metal to liberate hydrogen. It also reacts with base to form salt and water. So please remember, that is how it is different from alcohols. Now this question may be asked, why phenol is acidic? You know, acid means which provide H plus ion according to Arrhenius or according to Bronsted. Now phenol, if it gives you H plus, then it will be left with phenoxide ion. And we know any reaction will occur if the product formed is stable. So all processes occur to attain stability. So when we draw the resonance structure of phenol, we get 5 structures with oxygen attaining partial positive charge and ortho and para positions attaining partial negative charge. Whereas when we draw the resonance structure of phenoxide, we find that phenoxide itself carry negative charge, and the negative charge due to resonance is distributed over the ring at ortho and para positions. And very interestingly, oxygen never develop a positive charge here. So when we compare the stability of phenol and phenoxide, the conditions how to calculate the stability was given to you in class 11 when we did resonance. So we make use of that concept. So first of all, in phenol there is charge separation. You see, there is charge separation. We began with the neutral molecule, but in all the resonance structures we have positive and negative charges. Whereas in phenoxide we began with a negative charge, and in all the structures we have only one negative charge, no positive charge created anywhere. So there is no charge separation in phenoxide, whereas there is charge separation in phenol. And according to the conditions of resonance, the structure without charge separation is more stable than the structure with charge separation. Second point is, according to the conditions of resonance, you know that more electronegative element should hold negative charge and more electropositive element should hold positive charge. But in phenol we find that oxygen being more electronegative and carbon being less electronegative, oxygen is holding a positive charge and carbon is holding a negative charge, which is according to the conditions of resonance do not impart much stability. But here in phenoxide we find that oxygen developed a negative charge, but it never developed any positive charge. So combining these two effects, we find that phenoxide is more stable than phenol. So how phenoxide is formed? Phenoxide is formed by donating a proton by phenol. So since phenol is donating proton to attain a more stable phenoxide ion, hence phenol is an acid. Next we find the effect of substituents on acid strength of phenol. That means if we have electron donating or withdrawing group in the benzene ring, how does it affect the acid strength of phenol? For this I would ask you to refer to table 11.3, where you will find the acid strength of phenol in terms of pKa. Now what is pKa? You see, any acid can be represented as Ha. And according to Arrhenius, if you treat acids with water, they form hydronium ion, and with the formation of A minus, that is the conjugate base. Now, according to law of mass action, The equilibrium constant K will be written as concentration of the products divided by concentration of the reactant. Okay. Now organic acids being very weak acids, concentration of water is much higher than concentration of acid. So water concentration is taken to be a constant. So we take this water together with the constant and we get K into H2O equal to concentration of H3O plus into A minus divided by concentration of HA. Now K into H2O gives us a new constant, that is Ka, equilibrium constant for acids. A stands for acids here. Now you find that concentration of acid Ka value is directly proportional to concentration of H3O plus. So we know that higher the Ka value, stronger is the acid. Now you know Ka value being very small number, because the concentration of acids are very low, it's very difficult to calculate. So instead what is done, to avoid this we take pKa, and what is pKa? pKa is negative log of Ka. So you can see pKa is equal to log A with a negative sign. So what will be the proportionality? Higher the Ka value, lower will be the pKa value, and higher the Ka value we know stronger is the acid. So lower the pKa value, stronger will be the acid. So I request you to go through the table very carefully. So when you have electron withdrawing groups at the ortho and para position, strength of acid of phenol becomes more, and if you have electron donating group at ortho and para position, the acid strength of phenol decreases. And if you have electron withdrawing group or donating group in the meta position, it doesn't affect the acid strength much, because as you can see in the resonance structure of phenol, meta position never developed any negative charge. So if you have withdrawing group or donating group in the meta position, the negative charge doesn't get affected much. The next reaction under the same category is esterification reaction. This reaction we have done earlier also with alcohol. It is very similar, and here you have to remember, normally what happens, esters are formed by acid and alcohol, but here phenol, if you consider it to be the alcoholic part, it doesn't react with carboxylic acids to give you ester, because the reaction is highly endothermic. You can see here it's written the reaction is highly endothermic. So lot of energy is needed to carry out the reaction. So the reaction becomes slow. Now to carry out the esterification reaction, we take derivative of acid, that is usually acid chloride or acid anhydride. So acid chloride, when we treat it with phenol, we get ester and HCl. Now HCl is a strong acid and the reaction is reversible. To shift the equilibrium towards right, we take a base, that is pyridine, which will react with HCl to form pyridinium chloride to shift the equilibrium towards right. The next category of reaction is electrophilic substitution reaction. From the resonance, you have seen that phenol acquires negative charge in ortho and para position. So you can easily understand that phenol will undergo electrophilic substitution reactions at ortho and para position. So the first reaction we consider is nitration reaction. Normally for nitration reaction, what we need is concentrated nitric acid and sulfuric acid mixture. But interestingly, in case of phenol, since the resonance is very evident, very fast, it activates the ring very much. So with dilute nitric acid itself, we get orthonitrophenol and paranitrophenol products. In case you add concentrated nitric acid, all the three ortho and para positions get substituted and you get 2,4,6-trinitrophenol, which is commonly known as picric acid. Now this picric acid is used in explosives, but the quality of picric acid we get here is not very good. It forms a tar compound. Tar means very sticky black mass. Okay, picric acid will be a solid yellow compound. So we'll do later how to prepare picric acid in a better method. Now there is an exercise question. How do you separate this mixture, ortho and paranitrophenol? So you can see here in orthonitrophenol, The phenolic group and the nitro group being in the adjacent position, they form intramolecular hydrogen bonding and they exist as discrete molecules. Whereas if you take para-nitrophenol, the OH group and the NO2 group being very far from each other, they cannot undergo intramolecular hydrogen bonding, rather they undergo intermolecular hydrogen bonding. As a result, different molecules come very close to each other, and for separation, if you want to carry out distillation, you need more energy to break the hydrogen bonds. So para-nitrophenol will have a more boiling point compared to orthonitrophenol. So that is why they can be separated by a method called steam distillation. Please check the question in the exercise 11.8, and very important, very frequently asked question. So that's how you should write the answer together with the structure. Now, how do you prepare picric acid by alternative method? In your textbook, they have given only the statement, the reaction is not given. So please check, you have to carry out sulfonation reaction with phenol, but unlike other sulfonation reactions, it doesn't give you mono-substituted product, it gives you di-substituted product both at ortho and para position. Name of this compound is phenol 2,4-disulfonic acid. Now, this compound, when you treat it with concentrated nitric acid, you get picric acid. When you prepare picric acid this way, the yield is quite good. That means the quantity of product formed is quite good, and the amount of product, the quality of product formed is also quite good. So this is definitely a better method to prepare picric acid. Next is halogenation reaction. Depending on the nature of the solvent, phenol gives you two different products when you carry out halogenation reaction. We have taken halogen as bromine. If you take a non-polar solvent, then just like any other electrophilic substitution reaction, you get ortho and para product. Okay. But if you take water as the solvent in presence of a polar solvent, then all the three positions of phenol get substituted by halogen, just like nitration reaction. So here one more thing I would like to bring to your notice. Normally for halogenation reaction you need a Lewis acid catalyst, but for phenol you don't need a catalyst here. The reaction occurs even without a catalyst. You see here nowhere is written anhydrous aluminum chloride or any other Lewis acid catalyst. Then so I think we'll stop the video here. Kolbe's reaction and rest of the reactions will be discussed in the next video.